Welcome back. This lesson we're going to be talking about combined stresses, and in particular we'll focus mainly on combined axial and flexural bending in members, okay, whether it's a column or a beam with some sort of axial load. Typically members that are parts of frames will experience this kind of behavior. Now there are a lot of combined effects out there that AISC looks to handle, whether it's flexure and tension or flexure and compression or shear and flexure or any number of different scenarios, but we're going to focus mainly on the requirements for combined axial and flexural bending. All right, so this could be tension or compression. That's kind of the intent of what we're going to look at. All right, now to handle this, AISC makes some assumptions, okay, and I've broken them down into some categories, and we'll kind of go through these one by one and so forth and so on. All right, okay, the type of section plays a big role in this. Okay, so you'll be looking for keywords for things like doubly symmetric or singly symmetric, or others, as the case may be in section H. Okay, for this particular example, we're going to limit ourselves to the doubly or singly symmetric. This would include things like, you know, the W shapes, the S shapes, or even, you know, the channels, if you will. Okay, things like angles and those don't work quite as well with this particular approach. All right. Other factors that will affect this include the end conditions. Now, as we've explored with columns, a lot of the buckling calculations for the axial compressive effects on columns were based off of the end conditions. Okay, Euler assumed that compression was involved with pin-pin support conditions, and that one end could not move relative to the other. Okay, which leads us into a situation called drift or side sway or something like that that we'll talk a little bit more about, but those become a major factor. For a lot of what we're going to do here, AISC just says simply take K equal to 1. All right, so we're going to assume a non-side sway case and that it's perfectly pinned, and this is the most conservative of the assumptions, right? Because typically for a brace frame, K is something less than 1. If it's fixed, it's 0.5. Pinned is 1.0, so this is pinned. Kind of the scenario that we're looking at there. All right, okay. Kind of along those lines with the K factors, we'll be looking at you know, what kind of frame are we dealing with? Is it a braced frame? Is it an unbraced frame? And depending on the answer to this, your calculations can become a whole lot more difficult. All right, so kind of refresh our memory on what a braced frame is. Perhaps we have just a simple frame that looks something kind of like this. All right, I've got a column and a beam, another column, okay, and a brace frame can form in a couple of different ways, right? I could put a physical member such as an X brace or a K or a V brace or something, but something that locks this point to this point and this point to this point. This frame cannot deflect much. It'll still deflect a little bit, but I don't get much of a side sway situation here. Okay, or the idealized way in a lot of theory is that we draw it as a frame like this, and then I put a support here that basically locks this point. Okay, and if this point can't move, then this member, assuming that we don't allow it to deform axially, which is a common assumption, means that this point doesn't move either. So this frame isn't going anywhere. That's our definition of a braced frame. Okay, unbraced is a little bit uglier. Okay, and so here's what we're going to talk about. All right. Okay, so the idea is that an unbraced, or what we call as a moment frame on here, basically relies on the moment capacity of the columns and the beams to keep this system from drifting. All right, so imagine that I have, you know, I call this I've got a couple of different P's here, so let's do a P2 and a P2. I have some sort of vertical load that's loading this column, all right, and then I get hit with a lateral load, whether that's coming from seismic or whether it's coming from wind or whatever the case may be. But the idea is that this load here on a moment frame will cause this whole system to kind of shift over, where this point and this point will move by some amount that we're going to call as delta. Okay, and then likewise, if same assumptions we made before, if we don't let the beam change length, then the delta that's here is going to match the delta that's at the other side. Okay, well, here's what happens in an unbraced frame. Imagine that we've got our column here, okay, and that originally it was in this position, and then whatever the loads were, whatever the internal moments caused this thing to drift sideways. Well, remember that we had that axial load, our P2 there, But when it deforms, all of a sudden, if this point is pinned or fixed or restrained and this point drifts over, now this guy goes eccentric, okay? Before, the load was here, all we had was just a pure axial case, but now it's eccentric, and I end up with an additional moment due to this lateral side sway effect that's in the amount of something on the order of P2 times delta, okay? And this is what we call a second order effect because it's kind of a circular mechanism, right? This thing starts to deflect and the load pushes down on it, which increases the moment, which causes it to deflect more, which increases the moment, which causes it to deflect more, and you see the game that we're starting to play. Okay, so we've got to take, this is a very, very serious problem or a serious issue that has to be addressed or has to be looked at for most systems, okay? And these are what are known as second order effects, that the deformed position of the frame affects the internal loads of the frame, okay? And so we want to make sure that we're looking at and taking that into account as well. All right, and then the last major issue that we're going to look at then is what type of member are we looking at? Okay, so we're looking at a member that has some sort of axial. We're going to draw it as compression. It has a moment that's causing it to bend. Okay, well, depending on if my axial load here, my N, is very, very small on here, then this becomes more like a beam with just the moments on it. And this is an M1, this is an M2. It wants to do more of a flexural kind of thing. Whereas if M1 and M2 are very small, then it behaves more like an axial member, okay? And so the ratio of those guys to each other becomes a major, major factor in the way that AISC looks to establish the checks for combined stresses. All right, so that leads us to then our chapter H of our specification, okay? And the first thing they have you do, okay, and we're going to focus mainly on section H1.1, okay, in the 15th edition manual, okay? And they take a ratio of what is the applied load to the actual capacity, and if that is greater than 20% or greater than 0.2, they're going to call this as a heavy axial load. And the compatibility equation for the check then becomes something that looks like this. And you'll see that it's the ratio of what's applied to what it can hold, plus then 8/9 of the moment about the X to what it can hold in the X, plus the moment about the Y to what it can hold in the Y. And all that has to be less than 100. This is those 100% checks. These are like those stress checks that you did back in mechanics and materials, where the stress of this plus the stress of all of this can't exceed 100%. Right? And that seems pretty logical. Okay. The next requirement then is for B, okay, and that's the case where it's lightly loaded. So this is a light axial load. All right. Okay, and if that's less than 20%, then the formula is a little bit different, okay? And experimental tests have showed that this relationship approximates things a little bit better. But it's the same basic idea. That now I'm taking my applied load over double the capacity, plus then the ratio of these moments less than or equal to 1.0. Okay, now to kind of define the terms that we just saw, as we talked about, AISC writes it as PRs and PCs, okay? Because the book itself works with LRFD methods as well as ASD, and they wanted to make it so that the relationships all worked together. So you'll see a lot of what we're doing involves PR and PC, all right? So PR is basically the required axial strength, okay? And a fancy way of saying that in LRFD terminology is that's PU, that's the factored load, okay? These are the applied loads. The PC, which is basically the capacity, is the available strength, okay? It's how much load can the member itself hold. This is your phi-PN value, okay? And that's our capacity. Okay. Likewise, you'll see the MCs. Now, there were X's and Y's on this because depending on whether it's bending about one axis or bending about two axes, MC is the capacity, moment capacity, that's phi-MN. And again, if this is an X, then I put an X on here. And if this is a Y, I put a Y on here. Okay. And so those would be our relationships there. And then likewise, we'll put X's and Y's on this guy because I can have applied loads in different directions. Okay. This is calculated just the way that we did with beam analysis, doing the lambda problems or the LB problems. That's no issue. Finding phi-PN, no problem. We've got tables that help us with that, okay? And then even the required axial load is not a big deal to predict. This is the guy that causes problems, okay? This MR factor, right? Because if the frame is braced, I get one value. If it's unbraced, now I've got to start treating things a little bit differently, a little bit separated, okay? And so that gets us into kind of some side sway, second order effects as we just talked about. So If the frame is unbraced, then there are lots of different methodologies to use. They've got a tabular version in the AISC manual. They've also got a moment magnifier method, which is the one that I'm going to show you here. Okay, just because it's a little bit more logical, I think, and I can kind of wrap my head around what it is that they're trying to do. The tables work, don't get me wrong, but this is what I learned, and this is what seems to work well for me. Okay, so we'll be looking at then the Appendix 8, which is kind of at the end of the specification, section 16 in the book. All right. So here's how they're going to do it. Okay. According to Appendix 8 on here, all they're going to do for a second order analysis is they're going to inflate the first order effects and then add to it the increase due to the lateral effects. Okay, and so they're going to do that for both the moment and they're going to do that for the load. Okay, so what we have here is the first term in all this MNT and this PNT. These are all the first order effects. These are just your basic static analysis, or a lot of times what you get out of, a computer model that you run without considering P delta effects. These are just the basic static moments that are in it. Okay. The B1 is a coefficient. I'll explain that here in a second. And then B2 is another coefficient that's related to the lateral effects. Okay. And so it's these lateral effects are the second order effects that we talked about. As the column drifts over, the load causes an increase in moment. These are those increases. Okay. So we've got to be able to kind of separate those. So the analysis is already getting a whole lot more complex. Because again, as you change the size, the deflections change, and as the deflections change, the moments change, and that changes your size. And again, it's this huge circular problem, all right? So let's talk a little bit about what those factors are, okay? So the first one we're going to look at is the B1, okay? And the way AISC writes this is a multiplier for these P little delta effects, okay? And what this is basically a behavior of the member himself, okay? So relative to the member's endpoints, if I put a compressive load on this, it's going to want to bow a little bit if it starts to buckle, okay? And the amount that it bows is related to its stiffness, is related to the Euler equation, which we'll show you in a second, okay? And they always refer to this as the little delta, if you will, okay? And so it's basically what is he getting? Because again, if I cut a section, at the bottom, at the middle of this guy, and I cut him here, and this was my axial load, well, I know I get a normal, I know I get a shear, and I know I get a moment. And if that's some little delta, and that was P on here, P times delta is the moment, okay? And that's that moment that increases just from the bowing of this member, okay? Not even the applied loads. This is just the moments due to the axial load, okay? So we've got to kind of take those into account, all right? The B2 effect is a little bit different, okay? And this is the nomenclature looks very similar, but they call this as a P and then a capital delta, okay? And the capital delta refers to that story drift variable, okay? And the idea being that if I'm looking at a frame, in this case I have a portal frame with 3 portals in it, that if I put more and more portals on it, this becomes harder and harder to drift because every column is contributing some strength to the system. Okay, that, if I change the size of all 4 of these guys, I'll drastically increase delta. But even if I just change this one, I still change delta. Okay, so this is an attempt to try to capture the lateral information. Okay, and so that's why we call this as a story level type of approach. All right, so those are the difference between the deltas and the nomenclature that you'll see in the AISC manual. Okay, all right, so a little bit of the terminology that you saw in the equations. Okay, and I know I'm throwing a lot of just terms at you, and most of this is in the AISC manual, but just so we're kind of set up, when we get to the example at the end, I'll be able to show you. Okay, that the axial load from the restrained system, again, these are the Euler conditions, and the restrained system assumes pinned on this, okay, and then the moments that are in this thing as a result of the restrained system, that's your MNT. Okay, and again, you have X and Y directions on the moment, okay, and then like we talked about before, the MLT is an additional moment from the lateral drift, and then the PLT is any additional axial load that comes as a result of the lateral drift. Okay, all right, so here's how you calculate the values. Okay. I know it just seems like we're just kind of continuously going down the rabbit hole here, but it's not that hard, really. Okay, and so what happens is that the B1 coefficient, this is that first order coefficient that goes on the moment, and this is the CM characteristic, okay, and this is your moment magnifier, okay, and then 1 minus alpha times PR, okay, divided by this PE1 value, and you're limited to having to be greater than or equal to 1. You can't get less than 1. And that should make sense, right? Because if I go back to this formula and I make this term less than 1, I've just reduced the first order load effect, okay? So we don't want to do that. Okay, all right, so here's where all the pieces come from. A couple of terms that are in here. The first one is the alpha that's in this equation. It's 1.0 for LRFD. If you're using an ASD method, again, it's a typically different design approach than what we're using here. It's 1.6. Okay, and then the moment magnifier equation is just simply this formula of 0.6 minus 0.4 over the ratio of M1 to M2. Okay, and so what that is that's the end moment. So if I have an M1 and an M2 on this, okay, M1 is the larger of the two values. So if this guy is 100 and this guy is 50, M1 is 100. Okay, if it's the other way around, 50 and 100, then M1 is still 100. Okay, so even though I labeled these as 1 and 2, it has to do with the larger one gets the M1 definition and M2 gets the other one for these. Okay, and then if they have opposite signs, then we can take that into account as well. Okay, but typically a lot of times we just take CM as 1.0. Okay, and you're allowed to do that. Okay, all right. The next piece of what we're seeing in the equation is this PE1 value. Okay, and it turns out that that equation is just simply the Euler buckling capacity for the member. And if you remember, that's pi squared EI over L squared. Okay, this is for a mode 1. Okay, so we're looking at a column that's only bowing in a single direction. Okay, as opposed to, this double curvature kind of thing. Okay, so we're looking at this. This is the formula that causes single curvature. EI is the flexural rigidity of the member. Okay, and typically in most frame analysis, we just take that as EI. Okay, it's not this corrected term. So for what we're going to do, we're just going to take it as EI. Okay, and then of course L is the effective length in the plane of bending that we're looking with. So if you have a column that's braced at the midspan, the L changes, and so your Euler buckling capacity in that direction changes as well. But again, we'll show you that. Okay, all right, on to the next page. Okay, so nothing too major. Okay, B2 is a little bit more involved. Okay, and again, this is that multiplier for our P delta effects. Okay, so we've got our story drift, which is our delta, and so the formula for B2, go down here where we can see it, is written kind of like this, but it's kind of an interesting approach. Okay, it's 1 over 1 minus, there's alpha again, that's the same 1.0 for LRFD and 1.6 for AISC, and then they have this P story parameter, okay, divided by the buckling load of the story itself. Okay, and that'll be a formula that's down below. Okay, what P story is basically, it's how much load is this frame holding. So if this is P1 and this is P2 and this is P3 and that's P4, P story is the sum of all of those guys. So if you're, depending on what floor elevation you're looking at, if this is a multi-story building, these numbers change as you move down the building. Okay, and so it's the total vertical load supported by the story. Okay, and a lot of textbooks will write that as kind of a summation of the PI values, which would be, in this case, I equals 1 to 4. All right, and so that would be P1 plus P2 plus P3 plus P4. That's P story. Okay, and then the PE for the story on this thing, okay, is calculated as follows. Okay, if you have a system that is for stories with moment frames, okay, meaning that it's what we called as unbraced, RM is 0.85. Okay, and then it's 1.0 if it's a brace frame, meaning that we have no brace frames, we have some sort of other bracing, some stability provided. All right, so you're already taking a 15% penalty here. Okay, the total story shear is this H parameter, and what that is that's, if you draw the free body diagram and we cut the supports off of our system here, and I put a lateral load on this, then the entire story shear H is what's being used to resist the P value. Okay, so you do your analysis, and then I pull off what these values are for the total story shear. And this is against all columns. So if I have 3 columns or 4 or whatever, it's the sum of all of these little VI guys that are happening at the base of the columns. All right, so that would be V1, this is V2, and so forth and so on. Okay, and then H is just the sum of all of the VI. Okay. L is the height of the story. That's this parameter. Okay, so how high is it? How tall is the column? And it makes sense that L should be in there because he's definitely a factor in column capacity. Okay, and then delta H is our relative drift amount. Okay, and so what we do there is, let's imagine that we have a 2-story frame, okay, in which the first floor goes some amount delta 1, and the second floor goes some amount delta 2. All right, and then down here, delta was equal to 0 at the support. All right, this delta H for the first floor is delta 1 minus delta naught, okay, which in this case is just delta 1. Okay, delta H for the second story is delta 2 minus delta 1. Okay, so it's basically the amount of drift, because the idea being that if this guy is going delta 2, it went for a free ride with an amount of delta 1 based on what the rest of the structure is doing. It just kind of moved along. And so if we kind of draw this vertical line up here, it's that amount is all that we're accounting for. That's delta H. That's the relative drift at the second floor. Okay, so that kind of gets us to our terms. All right, so I know I threw a lot at you. Let's kind of walk our way through an analysis problem, okay? This comes out of one of the AISC design examples, and we'll kind of walk you through, and I can try to explain what it is that we're looking at, okay? All right, so what we have is we have a frame that has an axial capacity of 30 kips, okay? It has an X bending moment of 90 kip feet, and it has a Y bending moment of 12 kip feet, okay? We're gonna analyze a W10 by 33 column subjected to these loads. It's 14 feet long, and it's part of a frame that has no side sway, okay? Which basically means it's braced. Now, since we don't have a whole lot of information about the loading characteristics of the part of the frame that he's with, we're just going to arbitrarily assume that CB is equal to 1.14. This is a pretty low value, okay? And that's fine. But again, just for the sake of this example, however you calculate CB, you know, if you knew it, okay? So what we want to find then is this member acceptable? All right, so now what we have to do is we've got to kind of get our heads wrapped around our coordinate system, right? So we're going to call Y plus is the weak axis. We're going to call X plus is the x-axis, this is the centroid, and so the loading on this then is a moment of 90 kip feet that causes this section to bend as a moment about the x-axis, and then 12 is the weak axis bending direction. Okay, all right. Now, next piece, we go through, we look up the table properties for W10 by 33, so we've got our area, our SX, ZX, IX, RX, SY, ZY, IY, and RY. These come out of the tables up in Chapter 1, and then you can pull, for 50 KSI, I can pull these off of the ZX tables in Chapter 3. Which that would be table 3-2, and you can pull those values off. Or you can work the formulas that are written in the specification as well, but it's for 50 KSI, it's just easier to pull it off the tables. So I pulled all that data for us so we don't have to kind of fiddle with our tables. All right, so here's what we're going to look at, okay, is that we can analyze for a couple of different ways. We know that we need the capacities, which would be the axial capacity, phi PN, and the phi MN. Okay, but we can go through the tables in Chapter 4 for columns, or I can show you. I want to show you a different table in this one as well. All right, so if I go to 6-2, oops, I lost my tab, which is a combined stress formula, you get a table that looks something kind of like this. And this is a pretty cool table, actually. Okay, this is actually the available strength for members subjected to axial shear, flexure, and combined forces. Okay, and I apologize, it's a little blurry, but you kind of get the idea. I'm on a really big table here. Let's get over to the W10s. Okay, they've got a lot of these tabulated for you, which is really, really handy. Okay, so that you can kind of have everything in one location. So if I go find my 10 by 33, it's here somewhere. Okay, there he is. Okay. So here's my 10, here's my 33. The way this table is set up is that on this side is all the axial information for the different weights. So 10 by 33, 10 by 30, 10 by 26. Then over here is the X direction bending associated with it, and would be the moment that the capacities are that come out of that particular value. But what's down at the bottom is kind of everything else. Okay. And so if we go through and we look, so for our 10 by 33, that was this first white column. So if I come down, we can see then that we have, our tensile capacity is 437 kips. And our available strength for tension rupture is 355. We even have our shear capacity here, and then we have our flexure about the Y direction here, okay? But you also get a bunch of other section properties that you saw in the column tables and even the ZX tables. Here's LP, here's LR, here's IX, here's IY, which are your moments of inertia, all things that you need to be able to calculate this next step. So these are kind of nice tables because they have everything kind of in one spot. Now, all this information is duplicated over in the other sections, in Section 3 and Section 4. but you'd have to kind of bounce back and forth between them, and it's kind of nice having them all kind of piled together in one. So this is pretty handy. And then we've also got our RY, or radius of gyration with respect to the Y direction, and then you've got that RX, RY in order to correct the table, because just like with the column tables, what they've done is they've tallied the axial capacity, the VPN value, based off of the least radius of gyration. These are KLY tables. Okay, so if your weakest direction is actually the X direction, you have to modify it and come up with that KLY equivalent that was the RX-RY ratio that we talked about in an earlier episode. All right, so these are all kind of nice and kind of handy to have. So what I did on this one is I went in, and since my lengths and my Ks are all the same, okay, and it's at 14 feet, all I do is I read down to 14 feet, and then I come across over to that value, and you'll see that it's 253. Okay, and so that then for our problem becomes, oops. For a length of 14 feet, for a K of 1.0, and this is LX, it's also LY, okay, 14 feet, and then VPN is 253, so we'll need that. That's the maximum axial capacity. So what you can see then is we can kind of look at, our load, and you see that we had 30 kips axial load on the column, and its capacity is 253. We're fairly lightly loaded. Okay, it's not like we're pushing 200 kips on that thing. All right, so now here's how you calculate those coefficients. All right, we're going to start off with B1. Okay, so we're going to take B1, that's equal to CM, 1 minus alpha over these two ratios. So we're going to do that for each direction. Okay, and so for CM, we're going to take it as 1.0, that's conservative, as we talked about. Alpha is 1.0 because it's the LRFD method. Okay, and then all I do is I calculate the Euler buckling capacity for the X characteristics and for the Y characteristics on this. Okay, and so for the X direction, it's pi squared 29,000 KSI is E. I take my IX, which was 171, and then I do 14 times 12, get my unit straight, and I square it, and I come up with an X direction capacity of 1,730 kips. Okay, the Y direction capacity is pi squared E I, and now it's an IY direction. Okay, so the only thing that changes is this number over here. Instead of being the IX, you plug in the IY, that was 36.6 for a table, and if I do the math, that becomes 371 kips, becomes that value. So all we're going to do then is we're going to calculate the B1X and the B1Y. Okay, so the B1X, the multiplier for the static moment, then becomes this ratio. It's the CM 1.0, 1 minus 1.0, here's my 30, which is the applied, over my 1730 in the X direction. So again, that's why I got to watch the X's and the Y's here. Okay, and if I do that, this value is 1.02, all right? They're not getting a whole lot of multiplier on this. It's a very small increase. Okay, and so all I do then is I take my MU that was applied, and I take my beta 1 times the MUX. Okay, now again, there is a beta 2 and an M1, LTX on this thing, but because we said it was braced, this whole term was 0. Okay, so we're only really playing with that first term on this particular problem. All right, so that's 91.8 kip feet is that particular value. Okay, go back and do the same thing for the Y direction. Exact same process, except the only thing now is instead of putting the X capacity here, you're putting the Y capacity, that 371 that we had. And if I do that, all the math says that my B1 in the Y direction is 1.09, so about a 9% increase on the Y moment. So that's 1.09 times 12, that was the Y direction moment, is 13.1. So nothing major on there. All right, so now we got to go in and we got to actually find out what the nominal moment capacities are. Okay, and this gets a little bit more involved, but even that's not real bad. Okay, so we're going to start off with, and this is kind of all review of what we did with the beams in our previous videos. Okay, we're going to figure out what range we're in, because again, we're looking at moment, and it was flat, linear, and then something that looked like this. Here's LP, here's LR, this was MP. Okay, and then we're plotting LB on this axis, the nominal moment, accordingly. So these are the three regions. I called this is region 1, this was region 2. So our LB is 14 feet. We saw that our LP values this was like 6.8 and this was like 20 something. So we know we're in this region here, it's zone 2. Okay, and so if it's zone 2, then I can calculate the actual nominal moment capacity. Now, I do need the plastic moment capacity in the X direction. That's Fy times Zx, so plug and chug. 1,940 is the plastic moment, and then I can calculate the nominal based on the unbraced length using this. Okay, and again, it's just plugging in all the values and doing the math. Now, we took 1.14 just kind of as an assumption. Okay, so I plug in my MPs, and here's another MP, and then 0.7 Fy times Sx, which is the elastic section modulus, 35. and then this iteration of LB minus LP over LR minus LP gets you this. And then, of course, as always, you're capped at NP. You can't exceed that. Okay, and so if I do that, the equation calculates out to 1,820. The NP was 1,940, so the lower guy controls. And so our MNX is 1,820. It gets us that, which is 152 kip feet. And then if I put my phi factor on it, because again, our capacities have to have phi on them, it's 0.9 times 152 is 137 kip feet is that X direction first order moment. Okay, all right, so our capacity, I guess. Do the same thing for the Y direction. Everything else is the same. There is one little change, okay, that the plastic moment in the weak direction of this, you actually take, instead of just being it's Fy times Zy, but instead you're doing 1.6 times Sy times Fy. So this formula is a little bit different. You may not have seen it before, all right? But for the weak direction of doubly symmetric sections, that's a modification AISC makes you make. Okay? All right, so if I plug everything in, you're going to find out 50 times 14 is 700 kip inches, and then it's less than or equal to 1.6 times 50 times 9.2. Again, these are all those table values that we looked up in the properties. All right, so this side is 700, this side is 736, so this one controls. 58.3 kip feet is the equivalent, multiplied by 0.9, I'm at 52.5 on that. All right, so that gets us to our moments on that one. All right, okay, so then, now that we've got all the parts assembled, now we gotta go in and we have to figure out, well, which of those two requirements from section H are we actually dealing with? Are we in the heavily loaded case or are we in the lightly loaded case? So all I'm doing is I'm taking PR and dividing it by PC, okay, which is a fancy way of saying PU over phi PN. So our PU was 30 kips, our capacity was 253, this number is 0.119, okay, and that's less than 0.2, so that means that the criteria of H1.1b controls, okay, which would be that formula. I mean, that's all there is to it. You do all this work just to do that one little check to figure out which formula you're in. Okay, and so that formula said that for when you're less than 20%, it's PR over 2PC plus the ratios of the moments to their capacities in both the X and the Y direction. So all I'm going to do is take all those values that we tallied up for us, and I'm going to calculate, 30 over 2 times 253. Again, that's the applied. This is the capacity. Don't forget the 2 that's hanging out there. Okay, and then we're going to come in and do our X direction ratios. These are the magnified ratios. So MRX, our magnified moment, was 91.8. Okay, and our capacity was the phi MN in the X direction, that 137 that we saw. And then the Y direction also contributes, 13.1 over 52.5. And then we ask the question, are we less than 1.0? Okay, and it turns out that if you do the math on this, it's 0.979. Okay, and that is indeed less than 1.0, so therefore we are okay for this column in this situation. Okay, so, and in fact, it's actually a pretty good design. You're at 98% of 100%. Okay, now, if you go through all of this and do your analysis for a different section, you find out this guy is like 0.65, chances are you could probably do a little better, and you might want to consider going and redesigning or choosing a different size to do your analysis. But that's kind of beyond the scope of what I was wanting to show here. I just kind of wanted to show you the methodology for how we consider moment magnifiers and how we consider combined stresses, and we do our checks for this one. So anyway, that's kind of the example. I wanted to kind of work through you. As always, if you've got any questions, leave some feedback down in the comments below, okay, and I'll try to get back to you. Or if there's anything that we can do to make the videos, a little more clear and more understandable, I'm always open to suggestions. So please just give us some feedback. Let us know. Be sure to subscribe to the channel, and we will keep the videos coming. So until next time, we'll talk to you all later. Have a great day.